Hello everyone. Today I have come up with a simulation of the path of a charged particle in a magnetic field. So here you can see a region of uniform magnetic field. This magnetic field is represented by these dots. These dots gives the direction of the magnetic field. It means the magnetic field is perpendicular to the plane of the screen and coming towards us. Okay. So here you can see the origin 0, and this upper vertical line represents the positive y-axis and the downward vertical line represents the negative y-axis. And uh, here you can see a small dot, which is the charged particle, which we are going to inject into this field, and we will see the path followed by this charged particle in this magnetic field. Okay. Okay. Now, before injecting this charged particle into this field, let's see uh, what is its mass, velocity, the charge, and the magnetic field strength values. So by default, the mass is set to 6 times 10 to the power minus 25 kg. Means the mass of the charged particle is that 6 times 10 to the power minus 25 kg. Velocity with which it is injected would be 7.5 times 10 to the power 6 meter per second, and the charge is 5 times 10 to the power minus 16 coulomb. So it is to be noted that the charge is a positive. Okay, it's a positively charged particle, and the magnetic field strength is 3 Tesla. Now let's see the path followed by this charged particle in this magnetic field. Okay, so it is clearly seen that the path followed by the charged particle is circular with the radius 3 millimeter. Okay, given these values, the radius of this uh, circular path is 3 millimeter. Okay, now let's see how does this radius changes if we change these values of mass, velocity, charge, and magnetic field. Okay, so this radius 3 millimeter is calculated by using the formula R equals to mp over qb. Okay, where m represents the mass of the particle, v is the velocity of the particle with which it is injected into the field, q is the charge of the particle, and b is the magnetic field strength. So when you see this formula, you can say that r, or the radius of the circular path, is directly proportional to mass, radius is directly proportional to the velocity of the particle, radius is inversely proportional to the amount of charge, and radius is inversely proportional to the strength of the magnetic field. Okay, so we will verify these expressions, these relations. Okay, from this simulation we will verify these relations. So let's see. Now, to see this radius is directly proportional to mass, let's keep other thing constant, velocity, charge, and magnetic field constant, and let's change this mass. Let's increase the mass. Here initially it is 6. Now let's increase the mass to 8. 8 times 10 to the power minus 25 kg. Now according to this relation, the radius should increase. Okay, so let's verify this. Yes, obviously the radius is increased. Previously it was 3 mm, now it is 4 mm, and here in the simulation also you can see the radius has been increased. So we can say that the radius of the circular path of the charged particle in the magnetic field is directly proportional to the mass of the charged particle. Similarly, let's keep other things constant and change the velocity. Okay, I will keep the everything constant. Now let me increase the velocity. If we increase the velocity, if previously it was 7.5, now let me make it 9. Okay, now according to this relation, the radius should increase, isn't it, since it is directly proportional. Let's see, the radius should increase. Okay, it is also verified. Yes, we can clearly see that the radius has been increased. Okay, now let's verify this. Radius is inversely proportional to the charge. Okay, R is inversely proportional to Q. So keeping all the things constant, let's change the value of Q. Okay, I will increase the value of Q from here 5 to let me change it to 7. Okay, here we get 7 times 10 to the power minus 16. Now if I increase the charge, then the radius would decrease. Okay, so this was our previous path. Then the radius should decrease. Let's say, yes, now look, this is the radius we got. So we clearly see that radius has been decreased. So this is also verified. Now let's verify this relation. Radius is inversely proportional to the magnetic field strength. Okay, to verify this, let's keep other thing constant and let's change the magnetic field strength. Okay, now if this time let me decrease the magnetic field. Let me decrease the magnetic field from 3 to let me keep it 0.5 Tesla. Then what should happen? Then the radius should increase. Okay, so this was our previous path, this one. Okay, now the radius should increase. Let's see. Obviously the radius has increased. Okay, look here, because we have decreased the magnetic field. So this relation has been verified. Radius equals to mv by qv. Okay, and we see that the motion of the charged particle in a magnetic field is circular. Thank you.